Okay guys, so today in this video we're going to talk about some of the properties of limits. So just remember that as I'm writing you can pause the video if I go too fast, or you can't fast forward because I prevent you from doing that. So you either got to pause the video or rewind it or do what you got to do, okay? You'll also see the video will stop periodically and a question box will pop up on the right hand side that says what questions do you have. So if you have any questions, make sure you put them in that question box. Because I make the videos on my iPad, you will see that like I zoom in and out and sometimes things get a little weird. So just do the best you can, and any questions we will talk about in class tomorrow. So in class today, I introduced you guys to the idea of a limit, and remember we're looking at that example of like the soccer ball, right? Or that soccer game, and at 4 minutes it was buffering, which is fine because we know what's happening right before and right after. So in order to help us solve limits algebraically, we have these 6 rules that will apply. So I'm going to go through the 6 rules with you now, and it's a little dull and boring. And then we'll do a few examples, and we'll look at limits from different sides of the value we're approaching. Okay, so that's the plan for these notes. So before I start going through the properties of limits with you, I want to just go through and identify what variables I'm going to be using. So I'm going to be using, let me zoom in for a second just because it's easier for me to write when it's zoomed in. So for my properties of limits, I'm going to be using the letters M, L, C, lowercase c, and lowercase k. And they represent real numbers. Okay, so negative 27, 18.9, pretty much the numbers you deal with are real numbers. And we're going to let the limit as x approaches c, remember, so again, c is one of our real numbers. So we're going to let the limit as x approaches c of our function f of x equal L. And we're also going to say that the limit, erase that, hang on, don't ever capitalize limit like I just did, I don't know why I did it. We're also going to say that the limit as x approaches c of a different function g of x is equal to m. Okay, so that's the notation I'll be using for all 6 of, for all 6 of these rules. Okay, so let's look at the sum rule first. So just a reminder, mathematicians are not so creative in English. So like when you see the phrase like sum rule, it probably has to do with adding 2 functions together. Okay, so this is what the rule says. If we have the limit as x approaches some constant c of the sum of 2 functions, that limit is going to equal the limit as x approaches c of our first function plus the limit as x approaches c of the second function. Okay, and then that is going to just equal L plus M. Again, we're just using what we defined L and M as here. Whoa, something weird just happened. Hang on. Whoa. I don't know what happened. Oh, okay, there we go. I fixed it. I know you were all very worried. So again, we're just using the values we have right here to define those terms. Okay, again, so if I just zoom out so you can see the whole thing, right? We have a sum. Oh, I'm going to change I always forget that I can like make it into an arrow. Okay, so we have the limit of 2 functions being added together, f of x and g of x, so that's the limit as each of these functions individually, which equals L plus M as we defined at the very beginning using our variables. Okay, so along these same terms, we can look at the limit of a difference. So think difference. When you hear the word difference, you should hopefully think subtraction. So I'm going to zoom in again so it's easier for me to write it. So we're going to do the limit as x approaches c of the difference of our functions, so f of x minus g of x. Where did my thing go? G of x. So again, using the same notation we used earlier, we can break that apart. So we're going to get the limit as x approaches c of f of x, I'm just scooting over, minus the limit as x approaches c of g of x, and that's going to get us to m. That's not right. That's not what it's going to get us to. 2L minus M. Okay, so again, same idea as before. We have two functions are being subtracted, so their answer is the difference in their values of their limit. Again, we're using our notation as we defined up here. Okay, so just if we continue this pattern, we're going to now talk about the product rule. So as we know, product means multiply, so we're just going to multiply our two functions now. Okay, so the limit as x approaches c of our functions f of x times g of x is going to equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x, and that is just going to equal the value of our two functions multiplied together, so L times M. Okay, so we're just going to keep on trucking. So constant, oh, this one's a little different. We're now doing the constant multiple rule. So this rule involves a constant inside of our function, so a constant meaning any value. So the limit as x approaches c of some constant k, remember I defined that constant at the beginning, times our function, we can just pull out that constant. So that's going to give us k times L. So k times the value of the limit. If you need to, you can also write it like this, k times the limit as x approaches c of f of x. And then you know that L is the limit as x approaches c of f of x. Okay, so constant multiple versus product of two functions, but they act very similarly. And then we're almost done, not of the notes, but with the rules. So the next one's our quotient rule. I'm just going to go pull up a different color. How about purple? So we're now going to look at the quotient rule, so quotient divide. Okay, so the limit as x approaches c of f of x divided by g of x is just the quotient of the two values of our function, so L times M, or L divided by M, and keep in mind that M cannot equal 0, because we obviously can never divide by 0. And then finally our last one is the power rule. So we're going to look at power functions, so meaning we have a constant in our exponent. So we have the limit as x approaches c of our function f of x raised to the power of k. Okay, again, k is a constant, so that's going to give you just L to the power of k. Okay, so we're going to use these three rules now to talk about how to solve for a limit algebraically. I know we talked about it a little bit in class today with that one example, but we're going to look at it in more detail now using these 6 rules, and obviously we'll practice more in class next time I see you guys. So, I'm just going to find my spot on my page again. Okay, so to evaluate, let's look here. To evaluate the limit of a polynomial and rational function, all you need to do is use substitution and the theorems above. Okay. That's all you need to do. If you stick to substituting things in and you follow those rules, you will accurately be able to predict exactly what's happening at different points in your function. Always, no matter what. Okay? So let's look at the first example. For example, let's look at example A. Okay? So I know that I need to figure out the limit as x approaches c of x times x minus 4. Okay, now, this function, x times x minus 4, is defined everywhere. Okay, for every x value, right? We're not dividing by anything, so our domain is not restricted. So this function has a value at 3. So when I'm accurately predicting what's happening really, really, really close to 3, I can just use 3. Because I'm so close to it, it doesn't actually matter whether I'm at 2.99999 or 3.00001. Right? I'm just predicting what's happening at 3, and I actually know exactly what's happening at 3 in this case. Okay? So, just because I want to make our rules really clear, we're going to break this apart to represent our two different functions. So in this case, our function is x, is our first function, and x minus 4 is our second function. And we're going to be using our product rule, so that third rule lifts it above. Okay? So I then know that the limit of this function as x approaches 3 times x, I can then multiply it by the limit as x approaches 3 of our other function, x minus 4. Okay, now I can reasonably say, if I think about my function y equals x, which is my function here, right? This is essentially telling me y equals x, that's a straight line. And that line's defined everywhere. So I know then that this limit is going to equal to 3 times, and then if I think about this function here, that function is y equals x minus 4, so when I substitute in 3 to my line, because that line is defined everywhere, I'm going to end up with negative 1, which is going to give me the answer of negative 3. Okay, so here is what I would like you to do. On your own, determine the limit for B and C. Okay, again, you're just using these rules above. Okay, so just do the very best you can, and we're going to start looking at those two questions when we start in class next time I see you guys. So the last bit of our notes today has to deal with one-sided versus two-sided limits. Okay, so if you recall in class today, I showed you guys that we could estimate the limit on a graph by using our left finger, like our left index finger, our right index finger, and I referred to it as the finger rule. And I said that as you move your two fingers along your curve, when they touch, that's the value of your limit. So the reason right-handed and left-handed limits are important is because sometimes your fingers won't touch. And that's going to give us a different type of scenario. Okay? So we say, and I'm just going to type this in here because it'll be a little bit, whoa, never mind. Psych. We're going to get rid of that because it's in my way. We're not typing it in. So when we say we have a right-handed limit, or we have a right-handed limit, that means, let me zoom in so I can write. That means that we're looking at the limit as x approaches c from the right. So let's write that down. Okay, so it's the limit as x approaches c from the right. I'm moving my thing over. Okay, and we denote we denote right-handed limits using a little plus sign. So we say the limit as x approaches c from the right, because normally the right is positive, like if you think of the right of 0, we're dealing with positive numbers, of our function f of x. Okay, so for example, if I want to figure out the limit as x approaches 2 of some function f of x, here's 2, and I know something like that's happening, and that's, I don't know, 2 and 1, so I guess I have a straight line in my function. So instead of using both fingers coming like from this way and this way, I would only care about the right side. Okay, so I'm only going to care about what's happening here, because I only care about the right side of my constant. What's the right side of what x is approaching? Okay, and then the left-handed limit is the opposite. So the left-handed limit is the limit as x approaches c from the left. And we use a subtraction sign above the c to denote it, because the left side of 0 is negative. Even though sometimes, like in this example above, 2 isn't 0, we still this is just convention. Okay, so when you see these little positive signs and this negative sign, like those mean something, so don't ignore them. Okay, so I'm sure you've all seen Mean Girls, and when a limit does not exist, it's because the left side and the right side are not equal. Okay, so for a limit to not exist, the left side of the limit and the right side of the limit need to not be equal. So if they are equal, then the limit exists. Okay, they have to be equal. Okay, the limit from the left or from the right has to equal the limit from the left. Okay, so when those two things happen, we would say the limit as we have a limit. Okay, when the limit from our right equals the limit from the left, we have a limit. If this does not occur, the limit does not exist. Okay, so the last thing that we're going to do is just the example 4, which now that I'm thinking about it, I hope it happens. Okay, so the last thing is example 2, not example 4. I don't know why we said that. So I'm just going to walk you through A, B, C, and D, and then you're on your own, friends. You're on your own. Okay, if you need to, you can add in numbers here to help you. 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. So we need to figure out, just if we look at the first one, the limit as x approaches 1 from the left. Remember, that arrow means, or that negative means from the left. So right here, we're approaching 1. Now, if you notice on our graph, nothing's happening to the left of 1, right? Like I have a gap here. So this limit does not exist. We don't have a limit there. It does not exist. But if you look at B, when I want to figure out what's happening as the limit is approaching 1 from the right, okay, so I'm going to follow again, I only care about the right side of 1. So as I get closer and closer to 1, but I stay on the right side of it, that limit is going to equal 2. Okay, so now I have to think, now it just wants the value, I wrote this worksheet, I just want the value as x approaches 1. But you already know if the left side doesn't equal the right side, then there isn't a value, okay? The other way to think about it is if your 2 fingers don't touch when you follow the curve, then nothing's happening, okay? Your fingers have to touch for a limit to exist. So it does not exist. Now we're going to look at the limit as x approaches 2. So from the left, I'm at, actually that's fine. From the left, I'm at 3. From the right, I'm at 3. So my limit here is 3. Okay. Now if I look at the next one, the limit as x is approaching 3. If I come from the left to 3, I end there, but if I come from the right, I end up here. Okay, so 4 is not the same as 3, so my limit here does not exist. So go ahead and continue the rest of them, and we'll check them in class next time I see you.